Hello, let's continue this contour integral. In the last video, we have calculated the value for this integral, but we skipped some important details. If you missed that video, you can click here to see it. So in this video, we will complete those details. Before we proceed, don't forget to subscribe my channel, turn on the notification, and give a like. Let's get started. Here is a brief summary for the results from the last video. We have done the integral on C1 and C3, as well as the calculation on the 4 residues. We claim the integrals on C2 and C4 vanish, but we haven't proved it. So we will go through the details for the integrals on C2 and C4, and we will show they are equal to 0. Here we start from the integral on the path C2, and we define this integral as I2. So for the point on C2, we write it into the polar form. Here, the capital R is the radius of the C2 circle, and we will let R approach to infinity later. And then we do the differential to find dz. So we plug them into the integral, then we got here. Our goal is to show the limit of I2 is 0 when R approaches to infinity. And this is equivalent to show the limit for the absolute value of I2 is 0 when R approaches to infinity. And then we take the absolute value on this integral. We know the absolute value of this integral is less or equal to the integral on the absolute value of this integrand function. So the idea is, if we can show this integral inside this purple box is 0 when R approaches to infinity, then we are done for I2. So first, we write this integrand function into this form. The modulus of I equals to 1, and the modulus of e to the power I theta is also equal to 1. So we got here. And then we plug in fz, so we got here. And next, we write the numerator into this form. So we will deal with this blue term. After plugging the polar form for z, we got here. And then we write the logarithm into this form. And next, we use the triangle inequality, so we got here. The modulus of I equals to 1, so we got here. For this integral, theta goes from 0 to 2 pi, so the absolute value of theta is always less or equal to 2 pi. And note here, when the radius r is sufficiently large, for example, when r is greater than 1 million, then we have 2 pi is less than log r, so we got here. And next, we put these two terms together, so we got this upper bound for this blue term. I copy them here. And then we plug in to replace this blue term. Here is the idea. We want to show this term is less than something, and keep going on this inequality chain. And finally, we got an upper bound. And this upper bound only depends on the radius r, not depends on z or theta. And then we will show this upper bound approaches to 0 when the radius r approaches to infinity. So next, we need to deal with the denominator, because it involves the variable z. So for the denominator, we let this term greater than something, and keep going on this inequality chain. And finally, we got a lower bound. Then after taking the reciprocal, it will become the upper bound. So first, we use the triangle inequality to write it into this form. And note for this term inside the purple box, we use the triangle inequality again, so we got here. And then we write it into this way. The modulus of z is equal to r. So we plug in to replace it, then we got here. And note here, when the radius r is sufficiently large, then the r to the power 4 will be the dominant term. So we can have the r to the power 4 over 2 is greater or equal to the r squared plus 1. And equivalently, we can write it into this way. And then we add this green term on both sides. So we got here. And we put this term upward. So we got a lower bound for this denominator. And then we take the reciprocal. And next, we plug in to replace it. So we got the upper bound for this integrand function. I copy them here. So first, we simplify the right-hand side. And then we plug in to replace this integrand function. Because this integral is respect to theta, and the integrand function only depends on r, so we can take this integrand function out of this integral. So we just integrated, then we got here. I copy it here. And we know the natural log r is less or equal to r. So we plug in to replace it. After cancel out the r squared term we got here. And then we take the limit on both sides. And we know the limit for the right-hand side equal to 0. So we are done for I2. The integral on C2 is equal to 0. Now let's look at the integral on the circle C4. And we define this integral as I4. So for the point on C4, we write it into the polar form. And here the little r is the radius for this small circle. And we will let r approach to 0 later. And then we do the derivative to find dz. So we plug in and we got here. So the idea is similar to the previous case when we calculate I2. To show the limit I4 is 0, it's equivalent to show the absolute value of I4 equals to 0. And then we take the absolute value and use the same inequality, so we got here. So for the integrand function, after we simplify it, we got here. And next, we plug in fz, and then we need to deal with this blue term. After plugging the polar form for z, and then we write the logarithm into this way. And then we use the triangle inequality. And note here, the modulus of I equals to 1. Because the angle phi is between 0 and 2 pi, so the absolute value is less than 2 pi. And note here, because this little r is approached to 0, so it's very small. Then after we take the logarithm, it will approach to negative infinity. So we need to keep this absolute value on this log r term to make sure it's positive. So when the radius r is sufficiently small, for example, when r equals to 10 to the power negative 10, then we have 2 pi is less than the absolute value of log r, so we got here. And then we put these two parts together, so we got the upper bound for the log z. I copy them here. And next, we plug in to replace the log z, so we got here. And here the idea is similar to the previous case when we calculate I2. But the difference is when we calculate I2, we let the capital R goes to infinity. But here we will let this little r goes to 0. And next, we need to find the lower bound for this denominator. Because here the little r goes to 0, so the details is a little bit different from the previous case. And again, we use the triangle inequality, so we got here. For this term inside the purple box, we use the triangle inequality again, so we got here. And then we write it into this way. Because the modulus of z is equal to the little r, so after plugging to replace it, we got here. Because the little r approached to 0, so when the little r is sufficiently small, for example, when r equals to 0.01, and then we have 1/2 greater than the sum of r squared plus r to the power 4. Or equivalently, we can write it into this way. And then we add 1/2 on both sides. So we got here. And then we put 1/2 upward. So we got a lower bound for this denominator. And then we take the reciprocal. So we plug in to replace the denominator. And then we got an upper bound for this integrand function. I copy them here. So first, we simplify the right-hand side. And then we plug in to replace this integrand function. because this integral is respect to the angle phi, and the integrand function only depends on r, not depends on phi. So we can take this integrand function out of the integral. And then we just integrate it, so we got here. I copy it here. And next, we take the limit on both sides. So we need to evaluate the limit for the right-hand side. And here we introduce a substitution. We let r equals to 1/x. So for the limit r approach to 0, it's equivalent to let x approach to infinity. So this limit is converted into this form. And then we write the log 1/x into minus log x. So we square it and put it into the numerator. Because this limit is infinity over infinity, so we can use the L'Hopital rule. And here for the numerator, it's still in the form of infinity over infinity, so we use the L'Hopital rule again, and then we can find the limit equals to 0. So we are done for I4. This integral on C4 equals to 0. And don't forget to subscribe my channel and give a like. That's all for today, and thank you for watching.